Hello, this is Dr. Amrupriya, Associate Professor Tripli, Rohini College of Engineering and Technology, Palkulam. We are discussing about the course Power System Operation and Control. In this lecture, we will be dealing with the automatic voltage regulator. So, what is an automatic voltage regulator? For what purpose it is needed? First, let us see about it. So, first let us initially start with the exciters. The exciters are necessary in order to provide constancy of the alternator's terminal voltage during normal, slow and small changes to the load variations. For this purpose, the alternators are provided with automatic voltage regulator. The exciter is the main component in the AVR loop. It delivers the DC power to the alternator field. It must have adequate power capacity, for example, in the low megawatt range for large alternator, and sufficient speed of response, rise time which should be less than 0.1 second. There exists a variety of exciter types. In older power plants, the exciter consisted of DC generator driven by the main shaft, and now modernized exciters have been tend to have either brushless or static design. So this is the brushless design. And then in this arrangement we can see the exciter consists of an inverted three-phase alternator which has its three-phase armature on the rotor and its field on the stator. Its AC armature voltage is rectified in diodes mounted on the rotating shaft and then fed directly into the field of the main alternator. The exciter modeling, in this case we are having a comparator initially. So what does a comparator do? It creates an error message. How the error message will be created? It will be comparing the actual output with the reference voltage. So obviously error voltage E is equal to V reference minus V. Assume that for some reason the terminal voltage of the main generator decreases. This will result in the decrease of V value. So obviously what will happen? The error voltage will increase. As a result of the boost in the field current, the D-axis generator flux increases, thus raising the magnitude of the internal generator EMF, and hence obviously the terminal voltage will also increase. If you are setting the V reference voltage at a higher level, it will also have the same effect of increasing the terminal voltage. So let us see about the mathematical modeling. Here we can see del E is equal to del V reference minus del V. Upon taking Laplace transform, we get this. For the amplifier, we know del VR is equal to amplifier gain into the error value. Take a Laplace transform of it also. So now while you are substituting, we get del VR of S is equal to Ka divided by 1 plus STA, the transfer function into del Vs. Obviously Ka by 1 plus STA is the transfer function of the amplifier. So while drawing the block diagram, we will get a block diagram like this. For brushless AC excitation system, we can also see that the VR value is equal to RE plus, actually this is nothing but the resistance and the inductance of the exciter. So this is how we used to model it. If there is a change in the del IE value, obviously there will be a change in del VR value. And next, while we are coming, this is exactly the modeling of the generator's modeling equations, right? So next is, it depends upon the torque value. So there, torque is generated by means of the excitation field current. So here it is del VF is equal to K1 into del IE. And let us take the Laplace transform of it, and we get the transfer function as such. Now we do have the comparator, amplifier and the exciter. This is the block diagram presentation. And next we will go for the synchronous generator modeling. Obviously generator modeling is nothing but it will consist of the resistance, the inductance values. So let us take it and let us have modifications in that, because we used to consider the omega values, the speed values depending upon the frequency and all these things when modeling. Finally we will get the block diagram representation of the AVR loop consisting of the comparator, amplifier, exciter and the generator field. So when we apply the block diagram reduction technique, we get a simplified form of the AVR loop as such. Now we can have the transfer function. This is the open loop transfer function, and when having a closed loop with a negative feedback, obviously we'll be getting a closed loop transfer function of the same. Here the open loop gain depends upon the amplifier gain, the exciter gain and the field gain.